All right, so here we start with the first paper of the day, titled Terpsicode Dance Tool. Presenters are Dr. Kate Sicchio, Zeshan Wang, and Marissa Forbes, which is not with us today, but it's part of the, it's collaborating on this project.
All right, thank you. So hi everyone, I'm Kate, and this is Z. We came from Virginia to be here. And we're going to talk about Terpsicode, which hopefully most of you saw the performance of last night. And really, this is more of like a artist, slight technical talk, less big concepts and theory in this talk. So I've been live coding choreography for about 9 years now. I think like some of my first pieces were around 2011. I've done this in a lot of ways over those 9 years. I've used pseudocode to type scripts for dancers. I've used Clojure, which I did with Nick, who's somewhere here, Nick Rothwell. I've used haptic feedback in wearable devices. So the very first ICLC, I had a dancer in a shirt that vibrated, the right sleeve and the left sleeve that I was live coding. And then most recently, I've been interested in using still images as a way of making choreographic scores. So when I say choreographic score, it's some sort of, it's like not quite notation. I don't use anything like Laban notation or Burress notation, but it is still something that the dancer is going to follow along, more akin to like a graphic score in music. And in my work, the dancers are not necessarily interpreting that exactly. It's an improv, right? So it's giving them a structure and a place to develop movement from in performance. So the most, when I started working with these images to make these choreographic scores, I actually first worked with a library called Dance Dirt for title cycles, made by Tom Murphy in New York, for me to do just this, to make patterns of images within title that then a dancer would interpret live. And this piece is called Moving Patterns. I performed it last year in Madrid. This is a picture from that. Might look similar to last night. But really, the result of that was like, okay, like as a score, yes, I'm making these images, and that's, and they're in patterns, and that's interesting, and the dancer's responding, and that's interesting. But the actual coding side was not exactly what I wanted as a choreographer. The limitations of title is that it's really for doing sound, right? And like, I didn't want to type in sound terminology. I wanted it to be like I was speaking to the dancer. I wanted to use terminology I would use in choreography. And there's no choreographic coding language, so we had to make one. So that was sort of the birth of this project, was I wanted to be able to type things I would say to the dancer and get a choreographic score from the computer. So instead of this project, even though we're making a coding language, is more like an art project or a performance piece. So the steps involved, I would say, are much less like from a computer science point of view and much more like a choreographic process. So one of the first things we did was actually just like sit down and like write out a bunch of different movement terms. And like, yeah, so this is what happened to the wall in my office. It just became covered in language for movement. And then we started, sorting has become a big part of this process, which I think is also a choreographic thing, organizing things. So things started to become organized in this way as well. So we have like clusters of movement terms, clusters of compositional terms, clusters of timing terms. And then all of a sudden this like things that might become part of a grammar started to emerge from this process. We also needed images. So we took thousands of images of dancer who's working with us, Marissa Forbes. And then we needed to somehow sort these, so we put them through a T-SNE. And it clusters the images based on similarities. So then we started getting these, groups of images. And then again, to be in there like as a working choreographer, we started then actually taking these clusters and by hand identifying them and naming them, rather than, using the computer. We actually, this took most of the process. Like actually deciding, okay, this is a cluster and that's called spiral, and this is a cluster and that's called lunge. But that's how we decided like what the actual images that we're calling would be. Also, it just felt like this is how we would work in the studio, right? We would work on some movement and be like, okay, this group of movement is what we're calling the fold section, right? So it still had that very much like human hand touch to it. Let's see, take over.
We kind of started out creating this code from all the images that we made and how we were grouping the folders themselves. And it's pretty standard trying to build a language from like a parsing syntax. And then it was just a matter of how we wanted the actual kind of commands to work. And then really it was about, as Kate said before, like just making it very like human and like choreographer friendly. So language itself doesn't, when you like type out the cues or the choreographic phrases, they're meant to be like readable. There's no symbols or any of that type, just so that it does kind of mimic how you would speak to a dancer, or like a dancer or trying to interpret some phrases that they were like being given just to go along with. So this is just an image of the syntax itself that we kind of built up. And then we parsed it using PyJS, which is just like something that will generate a JavaScript parser for this. There are a couple of limits to that. There's, due to the way that it kind of just like creates this parser, we kind of lost a little bit of control with how exactly it's going to create these things. So a bit of how we want the timing to go is not as stable as it should be. And then there are some limits with that are in the JavaScript itself with how the images are ordered and coming up. But the JavaScript is pretty basic to just enter in timing and then the folders or the files in the movement directories for the coder to like put in for the dancer. And then since all the images within directories are like decontextualized from the original movements when they come up, it's that's like for the dancer to interpret themselves. It's I guess before on that like large image, each grouping was parts of different movements that were like decided to belong together. And then the app itself is being contained on Electron, which just makes the like UI cleaner to look at.
So here's a short video of one of my dancers in Virginia sort of rehearsing. addition to getting this like visual score of images, there's like a few other instructions I give for performance. So one is I guess I'm like almost like a meta score for the dancer is the first maybe set of images, because I also like change sets during performance. Try to be exact as possible with that image, just to set up that relationship that like you are responding to these images as a way for the audience to sort of read the performance. But then as the piece progresses, I do expect the dancer to like stray and vary and do their own thing, and maybe they find like an interesting moment and they'll keep doing that rather than actually try to be like, I'm gonna do exactly what's on the screen. And there's a few reasons for that. Like one is I'm coding a person, so they should have agency. It doesn't make sense to make them do exactly what the computer's doing, because then why am I not just programming a robot or just having the sort of animation going, right? If it's going to be a person, there needs to be a human inflection on it. So it's very much about the dancer taking that and sort of running with it and doing what they will with it, or else it's not really a choreography for a person anymore. So that's really important to me, that's part of it, is that you see that this is a person making decisions as well as a coder making decisions. Yeah, I think another thing that's like interesting in this piece as well is that the way it's currently set up is that the audience and the dancer sees both the language and the image. And so that also means that there's like some room to interpret things. So like sometimes you see the words in particular before you see the image. I know this happened last night, like walk came up. So like Phoebe started walking and then the image came up. So that's like another way that the dancer actually has some agency in the work, but also like is this interesting thing, like what becomes the score then? Is it this code or is it this image or is it both? And that's like something I'm still like thinking about and trying to work out, like where, like how much is it that you need both on stage at the moment, and how much is it that it's just the image? Or if I go back, I've done a lot of text-based scores before, so am I just going back to those? Yeah, that's sort of like the questions I'm asking myself right now while working through this in performance.
So for planned feature developments for this kind of version of the language specifically is definitely like adding in the compositional commands, but I guess one thing about that is due to the nature of choreographic scores and how they're being interpreted by the dancer, I think a lot of timing-based work or more live coding is kind of, you have these orders and sequences of what you can access, and then with images, it's not necessarily that they do have an order. So there are many like compositional assumptions that you make when you do think about like creating something, but those don't necessarily apply to this kind of like way of creating movement and like having it be interpreted by another human being, and like how that carry out in that manner. And then perhaps like switching platforms just to fix some of the smaller bugs.
Yeah, I think for me, like getting these more compositional terms in is sort of the key to the future of this. Like right now it's still just like calling movement and some timing things with the movement, but it's not actually really getting into like, more complex or interesting choreography. Also, right now it's been done as a solo. I've done previous work with groups and duets. I started with duets a lot in the beginning. And by duet, I mean two dancers rather than a dancer-coder situation. I don't know how I feel about this language in a more group setting until we get some more of those complex compositional elements sorted. So yeah, those are sort of places to go with this. in the future. So yeah, thank you.
Sorry. Hi, thanks for your talk. And thanks for your piece yesterday. It was really nice to see that. But what you were talking about the settings of the performance and how you want to think further, if you need to be in the stage or not, or if the image and the dancer is the main thing or not. So I just want to ask you the challenges of presenting in live coding, within the live coding community. Because I think the settings within the live coding community they're very static. Sometimes you kind of move things, or you kind of move the projection, or sometimes the projection is super small. And obviously, because you're collaborating with dancers, like there should be more exploration in performance settings. So I don't know if you can share more about your challenges of working with this community.
Yeah, definitely. I think, yeah, that's a really good question, because I think there's aspiration in the live coding community that we're an interdisciplinary community, but in reality, it's really a music tech community. And that happens over and over again. Like, yeah, people forget that your dancer needs a space. They put monitors in the space. People, yeah, don't think that about, like, people always ask me, like, if the sound's okay, and I'm like, I don't care. Can you ask me if my dancer has enough space? Like, these things come up over and over again. Yeah, and like where I should be on stage, like everyone else wants to be in the center, like maybe with code face, right? And I'm like, actually, it'd probably be better if I was off stage, right? Like, so yeah, these happen over and over again in terms of presenting my work within these contexts. It's kind of, I just like, yeah, deal with it at the moment. Until like, yeah, someone makes me like the keynote and I get my setup and I have my rider, my tech rider, with my brown M&Ms. But yeah, it is a challenge. And I think also, not just that, but also what people expect to see on stage. So like the text thing is actually part of that, right? Like what if I just took away the text? Like would people in the live coding community be upset because I'm not showing my code? And I've had that, like, with the haptic work I did at the first ICLC, I did not show my code, and, like, I had a certain professor of computer science yelling in my face about not showing my code, who's not here, but because that's so embedded in, like, that's what live coding is showing your screen. So that's all, but I was like, that piece shouldn't show its screen, like, the dancer is the screen, and particularly in that one, I was like, it would be wrong to show the code. It would be, yeah. So yeah, these are big challenges, but I just do it anyways. I just push through. Yeah. Thank you. Yeah.
Hello. Thank you for your talk. This clarified me a lot what I saw and heard yesterday. I'm curious about what do you think about the artistic process in between art and technology. You have exposed, both of you, an artistic part and a technological part, and maybe the artistic part was also a technological aspect of your process. You say a provoking phrase like coding a person. I wonder, and it's also a personal question, in this process of art and technology, it's supposed that now this relationship is have the boundaries blurred, but I'm sitting peer chauffeur, like in, maybe it's not blurred yet, but it's just apparent between equations in the science and intuition in art, maybe now algorithms in the computer science and intuition in the art. So I wonder about the in-between art and technology in your process? What do you think? Is these boundaries really blurred, or is we're still moving, jumping between art and technology, or they are really blurred?
Yeah, that's a great question. I think, yeah, there's like this aspect that's becoming more blurry, but it's still very, I feel like a lot of my work is about finding a way to make dances with technology, right? So it's maybe not actually that blurred. I'm like taking a technological thing and applying it to art. Because for me, I'm like, well, what can technology bring new to the dance making process? Like, I'm not interested in doing a dance where I like wave my arms and I trigger a sound. Like, that's been done a million times over, and it's just like this art tech, dance tech trope now. Like, here's my connect. And like, that doesn't actually do anything for choreography. I can do any dance in front of a connect and the computer will see what it sees. But what becomes more interesting in this process for me is that algorithms might actually change how I make a dance. And maybe there's something in that will actually make a new choreography that I wouldn't have thought of by myself. And that's sort of where I am in terms of like using technology in my process, is like, I want to apply this to dance making and see if I can change dance making in the dance. So I think, yeah, I'm getting to more of a blur by doing that. It's definitely more of a blur than the, triggering samples with movement kind of thing, which to me doesn't say anything about dance. But I still think there's more to go. I think there's like, and it's really hard in the dance community, I think, because there's everyone thinks that technology is somehow going to take over the body and take place of the body. And that's like another reason why like coding people and like people having this like agency in it is so important, because like I'm not taking that away. I'm just finding a new process of getting there. If that makes sense. Yeah. Thank you. Yeah.
Yeah, thanks as well for last night's demonstration, the performance. It was great to get an insight before we hear how it works. I'm struck by the last portion of what you just discussed in relationship to trying to give the dancer more agency, because it hints at perhaps an opportunity that is yet to be explored. And one of the things that strikes me and struck me last night also was the sense that there is a particular focus on the image, on what the dancer ends up looking like, or if I understand that correctly, which sort of presents sort of maybe a challenge to the audience for a compare and contrasts paradigm, which potentially doesn't play into what you've just described, where there is a compare and contrast even in the kind of the one-to-one mapping that one gets in so much of the interaction design sort of NIME community work. Is there perhaps an opportunity to completely remove the sort of ocular-centric quality and instead present a challenge to the dancer that is more about the choreographic? So the instructions are far more abstracted, that there's a sense of wonder between the call and response that you have.
Yeah, so I've done a lot of work with that in my pseudocode pieces. So like things like, what happens when you tell the dancer to dance blue, right? So it does become much more of like just a starting point for them to go and explore. Or like, if right hand blue, left hand purple, like things like that. So I have explored those kind of things as a way of like, giving more inspiration, I guess. Those, I would say, create like a looser improv, and they do highlight the dancer's agency much more, but it's much less than about sort of choreographing the work and just giving them places to play. So it's fruitful, but in a very different kind of way. Yeah. Mm-hmm. Yeah, so that's. I'm not talking about as abstract as. Yeah, no, so that's also part of it, like, why images aren't interesting is because, like, the in-between the shapes, the dancer has to create, right? So that's actually where they're dancing. And so like in some performances, you really don't see stopping in those shapes. You just see sometimes they hit them in between while they're moving. So it really depends on the dancer and the day, if you really get that. But yeah, it's almost like tweening, right? From when we used to animate Flash, right? And it's, yeah, there's just these like keyframes that they sometimes hit. So yeah, that is part of it, and part of the reason for the stills is that they're just like, yeah, anchors really, and that everything in between is really the dance, yeah.
Yeah, it actually relates really closely to what's been said, which was something to do with a question of what the code can't articulate, or oppositely, where are the points where improvisation of the performer really starts to arise. And again, I was really struck by the transitions in the performance that I witnessed last night. And I suppose there's something also about this kind of relationship between the word and the image. I'm kind of saying the same thing as what you've just said, really. I mean, the thing that strikes me about the image is that it's one moment, it's quite a discontinuous moment within a movement sequence. But the thing that also struck me about the way that you're using language within the coding is that it's really wide, it's very stretchy as a term. So the way that you use walk or the way that you use spiral, I think actually has the capacity to hold the whole of the arc of that movement from its kind of incipience through its beginning, through its arcing to its end. So yeah, maybe it's more of a continuation of this kind of discrepancy between the discontinuous possibility of the image and then the way that the word can hold more of an arc. And maybe there's something there also about kind of whether the work is deliberately exposing the deficiency of the image and how, in a way. Is it critical in that sense?
Yeah, I think that's part of it, is like it's a weird, because it's not a gesture, right? It's just this like weird frozen thing, and we're so used to talking about, the words are gestures, right? The words are, fold and lie down. Like the words contain much more than the image, and that's, part of this like weird thing that's happening with this as it stands right now. So there's something there too about, this, and what's interesting though is the stills actually all come from movement, right? They're not like posed, right? Marissa improvised and we did this like time-lapse process. So they're all grabs of movement. So like we were thinking of it almost as sampling movement, but it's more like, it's an even more finite level than that, because a sample has much more of a gesture in it, I would say. Like a sample would be like a short video clip maybe. So maybe this is like granular synthesis of movement or something like that. Like it's on a much smaller thing because it's just like this one grab of a movement. But then it's called upon as in the language as a bigger gesture. Yeah.
All right, we're running out of time. We have to move on. Okay.
All right.
Thanks, Kate.
Thank you.
Thanks, Frank.
I hope so. Let me check. Okay. Oh. Okay.
All right, so the Mégra
Mégra.
system, small data music composition and live coding performance. Niklas Reppel.
Okay. Wait. Sorry. Okay. Talk. PDF. Should be this one. Okay. My resolution just got fucked up, I'm sorry. Weird. Okay, then no full screen. I'm sorry, somehow the resolution doesn't work right now. I'm Niklas Reppel. I'm here to present my live coding system and also the ideas behind it, or I try to focus mostly on the ideas behind it. I work for the audio research group in Eurecat in Barcelona, who generously sponsored my trip here. Thanks for that. So, just to jump into it directly, why small data? It's a bit of a tongue-in-cheek response, a slightly defiant response to the big data trends that are happening right now, that basically are mostly focused around very big data sets and specialized hardware and very long training times that won't fit into live coding performance. Actually, probably be done by the time your model is trained. So in response to that, a lot more democratic use of machine learning methods might be everything that you can do with a tiny data set or regular hardware, real-time feedback, everything that you can do within a live coding performance, which most of the people here do. So how does this refer to Mégra? It is basically an ongoing case study on how to use small data methods in live coding performance and how to use different machine learning methods that nowadays are so, basically if people think machine learning, they think deep neural networks, and there's older methods and other methods that can be used to do machine learning. So the Mégra language is a domain-specific language for live coding and composition that is working in the symbolic domain. It's more or less a notation system as opposed to a signal flow system. It's definitely symbolic domain. It's based on Common Lisp, and the model that is the fundamental data structure, the fundamental model that's employed in Mégra are so-called probabilistic finite automata, which I want to present. What are probabilistic finite automata? A flavor of Markov chains, which might ring a bell with some of you. Presenting you the mathematical definition just for credibility points. I'm going to jump over that right into the visual representation. And can I make this bigger a bit? Maybe. Right. I don't know. That's better. So as you can see, it's fairly readable if you think that an X is a snare, an O is a bass drum, and a dash is a hi-hat sound. You can easily parse that model as a human being and read it, and you have your states and your state transitions and the probabilities, which are here shown as the thickness of the transition lines. So why are those models, or why is this model nice to use in live coding? It's a bit old-fashioned, as you might know. It's been developed since the dawn of computer science. Norbert Wiener has been talking about them already, and but because they're so old, they had to run on significantly more limited hardware and environments than we have today. So they had to cope with very small data sets. They're fairly readable for human beings as opposed to neural networks where you have edge weights and activation functions and all these things. But if you look at a graphical representation of that alone, it doesn't mean much for a human being. And the two things that I really think are interesting are the manifold ways you can interact and you can have a conversation with the PFA model, which I will elaborate on later, but also the relationship to human expectation as encoded in the model, which I want to talk about. No, is there more? Well, okay, they have some disadvantages as well, of course. If you're the type of person who wants to expose the whole state of the live coding performance in the code, that might get hard. It's possible, but it's a little bit tedious after a while at a certain level of complexity. I'm not so sure about the expressive power compared to deep neural networks. That's up for debate, but for artistic exploitation, I would say it's pretty good. What do I mean by the relationship to human expectation? Well, David Huron wrote a book about how the expectation of the next musical event is shaped by the preceding events and how it's encoded in conditional probabilities. And contextual distance, contextual size, like how many events do I have to look back to see how the expectation of the next event is shaped. And most of the time, we have to look just a few events back, like to see what the next event will be, or what kind of events the listener will expect, so to speak, not what it will be. But well, there's also larger distances, like how you expect in a song a chorus or the next verse, but those can be left to the performer, I think, because we still want to have the ability to shape the dynamic arc of our performances. So I don't think that's a big problem. And just to jump on, what I found the most interesting things and how it's encoded in the Mégra system is the modes of interaction that you can have with the PFA model. So, here's the lost here. Sorry. Live coding the maybe I can that's way better. So to jump into the code, a model of interaction with the PFA model could be inferring it from rules. So you can state the rules as human language, say, okay, after every snare there's a hi-hat, after every bass drum there's a hi-hat. After a hi-hat you can either have another snare, another bass drum, or less frequently another hi-hat, but never repeat the hi-hat more than 4 times. And if you execute that, the sound. And this is actually the one we have been seeing in the presentation before. That's just the small PFA we had before. But you can also create them by hand. You can just draw the shapes and create the states and the transitions by hand and create them that way, if you want to have very low-level control over what you're doing. You can also formulate them as human language. And that might look similar. Very small generator. Already got variance. You can also train the same model from, or, well, you can give abstract descriptions of what you're doing, like create a loop from bass drum and snare, just to stay in the domain of creating beats. And can find very short abstract syntax to create the same thing from a loop, or from any abstract descriptions. Or you can say like, give every event a 70% chance of being repeated, but never more than 4 times. Okay, doesn't sound that interesting right now. And well, you get a more complex generator here that has some states aren't used here, but as you can see, you have some repetitions, and the visualization is a bit sloppy here because I didn't put the content in it. But the interesting part is you can also work with data, so you can infer the same model from any bunch of data, do some kind of data sonification if you want to, like here, some random snippet from the cat genome. Probably looks cuter than it sounds. So we can shape the same model through data the same way we could shape a deep neural network through data, but we would need to wait until it makes sense, or it takes time to train, and it doesn't always run on your hardware. I've been recently getting into TensorFlow and these kind of things, but when you start, you always start in the cloud because you most likely do not have a GPU on your machine. Well, I don't have any, so you start with Google Colab or something and have to give up your data autonomy here, but the PFA model is fairly simple, so it can run on your local computer easily. Even though now we are getting into the region where it's not quite readable anymore. It's already quite a complex thing, but it's still, you can see like, okay, I have a state here that follows another state. And it's easy to fill that with meaning for the human reader if you would have some better visualization tools for that. So it's not as opaque as, let's say, a neural network. And, well, it allows for different modes of interactions. You can delete node, you can add nodes. So you can procedurally generate the same model, 5 minutes? Okay. Or you can take the model that you inferred from something else, like the beat, and just delete some nodes, add some nodes after a certain criteria that you set from the outside. So a loop with shortcuts, so to speak, grown over time. Of course, all these things can be automated. You can do time-based stuff that every so many steps inserts a node or deletes a node or whatever. So if you compare that to, let's say, big data methods where most of the times you wait. You enter your data, you try to shape your model through the data, you wait until it's trained, and then you can evaluate it, maybe with the exception of variable auto encoders where you can sample from the latent space and things like that, but still it needs time and effort and is very opaque compared to other models. So I hope I could convince you that PFAs are cool. I really like them. I've been working for them for a long time now. I mean, everybody got their preferred models. Some people prefer patterns, loops, PSECs. I like PFAs. That machine learning maybe isn't just deep neural networks, that it can be human readable and human interactable in different ways, and maybe that people might research this type of models because it's fun to work with data, it's fun to let the computer infer inspiring patterns and sequences from data, but it might be hard to do it in a real-time performance. Might change in the future, of course, but yeah, maybe there's hybrid models that people can develop. So that is kind of my pledge to the live coding community. Maybe somebody's interested in that. So thanks for listening, and maybe you have questions.
So it's in Stillbank Common Lisp. How hard would a scheme port be to embed into, say, extempore? Because it looks cool. I'd love to play with it.
I don't know really because I'm not a scheme expert, but sure. I mean, any language can implement it, but true. The basic model is probably available in some library already. I mean, it's widely spread. It's very well known, so probably not that hard.
Cool, thanks.
Thanks for that talk. I was just curious, you listed all those different ways to interact with it. What do you wind up going to the most when you're performing? Do you use all of them, or do you tend to have a go-to?
That shifts over time. I mean, of course, if you play an algorithm, then the easiest point to start is just to start with the loop and then work up on that and modify it and turn it into something more interesting, something generates more variation. I'm trying to force myself to use the learning methods to create tiny pattern languages based on this infer and the learning method and stuff like that. So I used it fairly often.
Thank you very much, Niklas.
The sound is already... Ooh, this is bad.
I can do it without the full screen.
Oh. Oops. Sorry, I'm trying to zoom in. I can't remember what's the key shot. 10% zoom. Oh, it actually doesn't go. Oh, there you go.
There it is.
1 second.
Yeah, maybe that's.
There you go.
Okay, thank you. Jesus Christ. Yeah. Maybe
You
I
do
should
it.
do it like this. No. Okay, hello everybody. Thanks to the ICLC organizers. Thanks to everybody to being here and lend me your ears for 15 minutes. Thanks to the working people of Limerick University and McMaster University that enabled me to be here. Okay, I am here talking about a project that I have developed with Diego Villaseñor de Cortina, and David Ogborn has been involved quite a lot in this thing as well. So what I am going to talk about is a platform or a series of platforms that we have developed that enable live-coded polytemporality based in the models, I guess, invented by the composer, artist, socialist artist, Colonel Nancarrow. Well, this was supposed to be a ASCII art of Colonel Nancarrow, but I guess we're not going to see it properly today. Yeah, there it is. Anyway, I mean, I feel that I'm repeating myself from the last conference, but so I will be brief about the context. So Colonel Nancarrow was an American-Mexican socialist artist, born in Texarkana. He lived through the, well, he lived in the south of US in the first part of the 20th century, so he lived through the Jim Crow era. He was somehow moved by it. Later, he became a member of the Socialist Party of US. That took him to go to Europe, fight fascism in the Spanish Civil War, return, being persecuted by McCarthyism in America, so he then had to flee, and he was given a choice to go to Canada or Mexico, and for some reason he chose Mexico. He got to Mexico, he started composing, and Mexico was passing through a very nationalist stage, so he was marginalized because his sound was too American for the Mexican music scene of that time. So he was 2 times marginalized without his nationality and without being able to compose in his new home. He secluded himself in a very cool house built by Juan Ogborn. And he just created this automata, a piano player, that was able to, well, explore music from a very particular perspective, a piano player. And what does a piano player can do that many other things cannot? Well, cool rhythms, cool temporal relationships, etc. So this guy started exploring that. He became famous in the 80s because Ligeti said that he was probably one of the best or the best composer of the 20th century. And then Mexico City became this space which North Americans, Europeans make this pilgrimage to see the great Colonel Nancarrow. And he started to become this fetish figure of elite academic music. At this point, the narrative of his life, well, nobody mentions that he's socialist and he was excluded from US, from Mexican music scene, and he was like claimed as a great genius. These have created a lot of narratives that are very dramatic and maybe too simplistic. Claiming that Nankaro was a genius, claiming that Nankaro was exploring the final frontier of music, making some sort of claim that Nankaro was a last modernist artist, exploring like the last possibilities of musical creation by allowing rhythm to go to the most radical ends of it. I am here to explore a different narrative of what Nankaro proposed. I am claiming that he enabled a space of possibilities that is new, and live coding is a good way of exploring this space. This space is polytemporality. So polytemporality means that we can play different tempos at the same time in very arbitrary ways and still make sense of it. Okay. So, me and Diego started working on this a couple of years ago. The first exploration that we did is the Canon generator in our nice organization called Nankinakan. Canon generator plays with the one fundamental musical structure that Colin Nankaro created. This is a tempo canon. A tempo canon is when you repeat a melody, let's say, or a musical structure 2 or more times, but with different tempos. And you align it with something that Colin Nankaro called a convergence point. So let me show you how this works. So here you can hear a same melody repeated 5 times in different tempos, so it is out of sync. Okay, so yeah, that's the idea of a tempo canon. Various melodies at different tempos, but aligned in something that Colin Nankaro called convergence point. So we started working with this, firstly as a pedagogical tool to understand better the ideas of Colin Nankaro, but then we realized that we could live code with this, and well, that became very interesting. So this is a very short demo of Diego improvising with one of the first versions of the Canon generator. It's not very clear, yeah? Go to full screen. So yeah, in line 33 you can see how this is made out of the same melody in different configurations, in different tempos configurations, and in different pitch transpositions. So, okay, this is our first stage of development. We presented this in the last ICLC. It was fun, but we thought that we could do something more interesting in many ways, no? Like ICLC, the last ICLC like activated a lot of things in our minds, and we started exploring weird new ideas. But at this point, I moved out of Mexico City. I went to Canada. Diego stayed in Mexico. So we were not able anymore to go Sundays, drink beers, eat tacos, and program, and think about things, no? So we have to come up with new strategies to develop this thing. And well, we decided to do what tempo canons do, diverge. So Diego started working in something that he called Fluent Can, and I started working in something called Time Note that I will expose later. And Fluent Can is like an adaptation of the Canon generator that allows you to live code better. So these are the characteristics of Fluent Can, and I will play a little demo that Diego prepared. etc. So yeah, Fluent can focus on live performances. It's a fluent interface. You can chain methods. It's flexible. It has a lot of emphasis on composability. And it is expressive, and it's very clear. You can see in the code what is happening very clearly. At the same time that he developed Fluent Can, I was developing TimeNote. TimeNote has the same core idea of polytemporality, but I just took it to another place, no? I was focusing on, I was doing a notation experiment, and maybe the most salient characteristic of this notation is that it tried to articulate duration, rhythm, and the idea of polytemporality, these canons that we were talking about. So I will play a little demo. Well, actually, you just heard this yesterday, so I don't know if the demo is, well, I will play it. Yeah, sure. So, okay, what is interesting about this is the rhythmic notations that I added to this. First, you can see that it lasts 8 seconds long, like the whole structure will last 8 seconds. This is a duration parser, so I am just controlling the duration in this parser. In the second parser, where you have the XOs, XXX, X means onset, O means no onset, like a trigger sound or not trigger sound. And the 3 with an E in the middle and an 8 is an Euclidean rhythm generator. And I am making a canon down. In the next line you can see RA, that means ration. So I am making a canon in which one structure will be 1.2 times bigger than the other one. Okay, I hope that's clear. Okay. That was us diverging. That means that Diego developed his thing, I developed mine, but in the middle was a lot of conversations. And what was interesting about this process is that he influenced me. Like, I have a lot of ideas that he developed in Fluent Can in TimeNote, and TimeNote influenced him a lot. A lot of ideas that were developed for TimeNote, he implemented them in Fluent Can. So we thought that this was a very interesting way of programming something like this. So in the future, and we're already thinking about this. We're thinking converging again. We're thinking now developing a platform using Clojure as a base language. We're going to focus on pure time, polytemporality rather than canonic structures. It means that these 2 or more musical events in parallel will be organized as a canon, but they don't have to be canonic. They can be different now. As long as they're discrete events, this can be done. We're expanding to multiple convergence points. It will be very lazy. We will have acceleration, which will be very interesting. And I guess that's it. We thought of talking a little bit more about methodology, but I am running out of time. So these are the most selling characteristic of our epistemological stances. We move from a bidirectional influence, from time to Fluent, to a multidirectional influence. We're focusing on modularity and composability, and we're developing things openly and slowly. And something that I wanted to say that is very important is that resistance played a very fundamental role in this process. Diego didn't allow me to dominate the conversation, and I didn't allow Diego to dominate the conversation. I think this was very important. Anyway, maybe later we can talk more about it with a beer in our hands. And yeah, we created an Ankarowan Chaosmos to code the less. And yeah, thanks a lot for listening. That was it.
Thanks a lot, Alejandro.
Hi, Alex. Alejandro, thank you for the presentation. So I saw your presentation. Well, I've seen you present before some parts of this, and you always start, from what I recall, with a story about Nankaro. And so I just want to, maybe if you can expand a little bit how, you know, this history or story from Nankaro in terms of maybe how he was a socialist and rejected has influenced your work in these terms. I know you said something about the chaosmos and the resistance, but maybe you can talk a little bit more about that.
Okay, well, yeah, like Nankaro has a very interesting history, and it has been captured by academia to be portrayed as this magical genius, and his genius comes from some sort of realm over ourselves. Very, very opaque, very magical, the narrative. What I'm trying to say that, no, this is not magic. Like, his creativity and imagination comes from probably his isolation and his way of deferring, like his way of rejecting something that he was not able to endorse, I think. I think it's very important to rescue these social and political aspects of artists and creative people. Yeah, I don't know what else to say about this. Yeah.
Thanks. So I think you just started to touch on the same, but I'm really curious about this idea of resistance in terms of the dialogue between you and Diego, and how that relates to this sort of radical approach to creativity at the same time.
Oh, okay, yeah. I have the impression that, well, to keep referring to Byung-Chul Han, as in the keynote yesterday, we live in a society in which things tend to circulate in a very fast speed, in a very accelerated way. This tends to eliminate critical thinking. When I say resistance, many people have in their minds some sort of very solid, maybe militant definition of what resistance is. This definition might be something like the capacity to disarm your enemies or others' ability to harm you, no? But resistance in other contexts, particularly from Zapatismo context, is a space in which people dialogue, no? And the dialogue, yes, it is also a way of being vigilant, of not dominating conversations, basically, but it is also the idea of stressing ideas, testing them, no? Often I use I compare this with a chair. Like you present a chair, and someone else has to sit on it and stress it the more they can until it's almost about to break. I think this is a very important part of our process, like dialectics almost, no? I guess, very similar to that. We often tend to be very complacent. I don't know if that's a word in English. Anyway, I tend to allow ourselves to circulate our ideas very, very quickly, and I think it's often more useful to interrogate in depth what we're trying to do, and maybe think if this is the best approach or not, and maybe, well, stop us a little bit, no? Maybe be slower.
Thank you very much, Alejandro. We have to cut it here.
Okay, cool.
Yeah, thank you very much. All right. We're running a bit late, but you're good, yeah? So the next one is Liveness code and the DeadCode in code joking practice. Jamie Beverley.
Thanks. Great, thanks. Thanks for being here, everyone. My name's Jamie Beverley. I'm here from Toronto, Canada, to talk about Liveness code and DeadCode as they pertain to code jockeying. And before I jump into anything, I just want to say thanks to the Department of Computer Science at U of T, McMaster University, and the Networked Imaginations Lab for the funding to be here, as well as the conference organizers and the reviewers who gave really excellent feedback for my work. So my agenda for this talk, I'm going to talk a bit about the backgrounds and motivations for the DeadCode code jockeying software that I built. I'll do a quick demo and talk about the design and features of the software. If I have time, I'll talk briefly about the implementation, and then discuss whether what I've created still counts as live in code, and then conclude with some future work and to-dos. So code jockeying, as the name suggests, is a hybrid approach to live coding that blends live coding and disk jockeying. Often the aim is to transition between pre-written code snippets as opposed to writing new ones live, and exploring the new permutations and orchestrating their timely execution. Since this can be quite challenging with text, I think we've seen a lot more graphical softwares that facilitate this. To note too, there's a Visor environment that I think we were introduced to last year at ICLC, but also environments like Super Collider and its graphical abstractions like the node mixer or proxy mixer. If I could contrast code jockeying a little bit to blank slate live coding, blank slate live coding is when the performer usually starts from a blank screen, also known as scratch live coding. Emphasis is placed more on creating new material live, and often subsequently deleting it at the end of a performance. I make the argument in my paper that blank slate live coding has qualities of speed and ephemerality, as often the code is kind of this ephemeral thing that appears and then is deleted, which has paved the way for a lot of the celebrated danger and experimentation in live coding, but I think which also opens performers and practitioners to a form of precarity that is sometimes difficult to manage. In some of the earlier literature around live coding, I think some of the emphasis of code was articulating code as text. So in both of these quotes from sort of early 2000, there's kind of an implicit privileging of text-based code, whereas I think since then, and since we've situated live coding within the broader new media practices in computer-mediated art. We appreciate that code can be a lot more than text. We see graphical representations, esoteric languages, embodied in dance, weaving, just to name a few. I draw from Wendy Shun's notion of code as fetish to expand this thought a bit. Shun offers a fascinating caution against code fetishism, which posits code as the essence of new media and knowing software as a form of enlightenment, and instead prompts us to recognize how power and perhaps profundity exist at the intersections of social and machinic relations. In sum, then, I think we can say that we appreciate coding as more than just the text that we see on the screen. There's lots of things that go into live coding events, social and technical. I think Shun also offers really interesting insights in our conceptualizations of liveness, positing something as live and may erase the other things that go into creating a performance spectacle. If execution is the moment that everything comes into being, I think there's potentially an implication that the source code and the visible coder are the only actants in the broader networks that create things like algorithm performances. Drawing from Parkinson and Bell, who articulate how the perceived liveness of a performance is directly tied to the perceived amount of labor that the performer is exhibiting. I think I push back a bit against the articulations of liveness that privilege speed and in the moment efficiency over things like deliberation and slowness. And I found it really exciting yesterday, the keynote, the prospect of a sort of slow kairos, and Alejandro was also just talking about a form of slowness that could be part of live coding as well. And there is, that does appear too, like the slow code movement and things like that. I guess my personal struggle and caution is that to classify as live and improvisational, a live coder may be asked to exert greater labor live while also accepting that the results of their labor, the code that they create, is expected to vanish at the end of a performance. So all of this is kind of a long preamble to discuss the motivations for the code jockeying software that I built. DeadCode is a browser-based, language-agnostic, and tablet-friendly code jockeying interface that currently supports title cycles in Hydra. In several ways, when I was making it, it felt like I was deviating from both live and codeness. DeadCode was built with three sort of guiding motivations. The first was for the persistence and reuse of code. So that seems to kind of depart from earlier articulations of live coding, which really celebrate the live creation of code. And also my desire to go back to sort of graphical and gestural interactions that are kind of common to DJing. So I had sort of several crisis moments where I wondered if this really counts as live coding, and I invite that critique as well. So I'm going to jump into a demonstration of the software. It runs in the browser, so I can just open it up here. I'm greeted with this interface where I've got a grid of buttons on the left here. If I right-click on one of these buttons or long press on a tablet, it opens in the editor over here. Here I can write the code that's tied to that stem. So I can give a name to it. Maybe I'll call this my kick, and I'll put a title pattern that's just my kick. And if I toggle the button on, I start to hear that. Now the code box I've got here, I had to click evaluate to run it, but if I toggle this box to be live, I can also type and the results will be interpreted automatically. So if I do ×2, and we'll also notice below the editor here, I've got a few effects that I could apply to this title pattern. So I've got gain already applied to it, and I can adjust this slider in a more kind of gestural interaction. I can also apply other effects here. That one I've blocked somewhere. And then at the bottom, I can also specify code that gets kind of tacked on to the beginning of the title pattern. So I can toggle that on and off as well. So to give a bit more of a complete demo, I'm going to load a more complete set that I've already pre-composed. If I hold Control and hit L, this will load a set that I've already created. I've got a number of stems over here that I can toggle on. There's another tab over here that's called the Master tab. These are effects that are applied to all running stems. So, for instance, I could apply a filter to everything. And a lot of these interactions that are kind of common to DJing are supported. I also mentioned that it supports Hydra as well. So I've got a couple of stems down here that produce Hydra code. If I toggle one on, oops, I just have to push the state here. So if I toggle this on, and if I open it, over here, I've got a drop-down where I can select which language the stem is. Right now, it just has a very simple Hydra pattern. And similarly, I have effects that I can apply to it here. And I can overlay another Hydra visual on top of it. You'll see in the bottom here, I've got a very small and probably hard for you to see rendering of what the visuals would look like to an audience, as well as an overlay of the code that's being produced. I wouldn't show this to an audience because I'm hiding a lot of the code. So there's another view I can open. So the thought here is that the audience would be provided this code and visual projection while the performer would have this more graphical projection. But then I still, as a performer, have this little box that I can see what I'm showing the audience. So now I'm going to go back to my slides and just talk a bit about some of the features. So one of the key features that I just showed you in the demonstration here was an idea of having multiple projections of the code. And from this, I'm really drawing from Ogborn and all's work with Estuary, where there's an idea that you could have sort of one code set, but different projections suited to different contexts. So clearly the audience is provided one projection of the code, whereas the performer has a more more of an interface of a projection for performing. There's actually multiple projections available to the performer. So I showed you the desktop view, but I could just as well have opened this on a tablet where things like toggling on the stems are well supported by touch interactions. It's easier to tap those than it is to click with the mouse. Also, I have support for MIDI controllers, so I could map any kind of Ableton controller to this that has a similar button grid, and each of those buttons could map to turning on and off a stem in the software. I also have built in a concept of different levels of liveness, and again, I'm borrowing, of course, from Tanimoto's taxonomies of programming liveness, and also Estuary's embedding of those, of being able to toggle between different levels of liveness. So the first level is the sliders and those effects that I demonstrated. Those are all immediate, or perhaps level 4 liveness. The automatic code evaluation that I showed in the text editor, what I've called debounced liveness, because evaluation doesn't happen right when you enter a key, because I had it like that originally, but I'd have lots of errors, and I'd sometimes crash title if I had a malformed expression. So instead, evaluation happens some configurable amount of time after the last keystroke. And I call that the debounce liveness after the common JavaScript debounce operation. Then there's manual code evaluation in text editors where you hit Shift-Enter or the eval button, and then what I've called DeadCode, which is all the code that I've pre-written. This is the least live, but I think it still is worthy of mention as part of the code and the liveness. I also have an idea of, I'd like to make this as language neutral as possible. So right now it supports title cycles in Hydra. Languages that can be evaluated directly in the browser, that's great, it can do that. For languages like title cycles that aren't evaluated in the browser, the code gets passed from the browser to a Node.js application I have running on the machine, and that just pipes it to the appropriate interpreter. So that's the same approach as was taken with Extramuros, and that's fairly extensible. This is the architecture I discussed in the paper, but it's actually grown a fair bit. The main limitation of this was there was no concept of collaboration or sharing with this. There's just sort of one browser and didn't have a way to open another browser and have those two synced. So I actually shifted to something more like this, where at the center I've got a WebSocket server running a state machine, and then any number of connected clients, which are all running the exact same state machine. So the connected client could be my desktop machine, my tablet, my cell phone, and as well the render views that are shown to the audience. It was created in React Redux, and the WebSocket server was Node.js. Really benefited from the monolithic design. For example, the state machines that run both on the client and the server applications are the exact same code, so anytime I need to add new actions or new features to those state machines, it's just one place and everything inherits it. And then whether an event propagates from a client application to the other clients is just a specified field in the metadata associated to each action. I'm not going to talk too much about the code evaluation, but adding a new language really just requires writing the conversion between those stems and the effects and how they should turn into the code that it should produce. So for example, with title, if I have a ton of stems running, they all get composed into one big title stack expression, and that's what gets evaluated. Hydra is similar. It's like a big chain of blended visual layers. So in many respects, I was trying to deviate from the live creation of code. So it's fair to ask whether this still constitutes as live or live coding. To many coders, the default mode of live coding is improvisation. That doesn't explicitly prevent writing new code live, but I think it potentially does enable a lazy kind of performance where everything is pre-coded and I'm just triggering things. But at the same time, it opens new ways of improvising by seeing what the audience is responding positively to and engaging in that kind of curating improvisation similar to DJing practice. Secondly, with regards to the render view shown to the audience, that really requires a degree of trust with the audience that what I'm showing is actually an accurate representation of what I'm triggering in my environment. You could imagine like a nefarious render view where the code I'm showing looks far more complex than what I'm actually doing here. Maybe I'm checking emails or throwing cake. So that's something to consider as well. And whether or not it's code, DeadCode can be performed without entering any text code, but I think I fall in alignment with Shun, not trying to align the essence of something to just the medium of code, and also appreciating that code can be far more than just text. Those things like sliders can also be interpreted as a form of code. For future work and to-dos, these were listed in my paper. I actually was able to implement the first two, so there's capacity to collaborate with this. There's integration with hardware controllers. I'd like to create a utility for making it easy to create MIDI mappings. There's a ton of Ableton controllers that would easily kind of map onto the interface I've built there. I'd like to include more languages, and I think I'd like to start with a browser-based language. I really like the idea of being able to open this on an iPad, on the subway, and being able to create code and play around with it without needing a full computer. I'd also, if there's uptake of this and people enjoy using it, I'd love to create a backend system to support sharing and importing stems. I can imagine a performance where I browse a library of published stems by other users and grab a stem that someone published 5 minutes ago and stick it live into my performance. I really like the idea of that, and I think that could open a new avenue for some really cool improvisation. So thanks so much for your attention, and I'd love to take some questions.
So, yeah. One question about the, let's say, the multimodal way of working with your tool in a live situation. Does that cost you a lot of cognitive energy, or do you have any feedback on that? Because well, my personal experience is switching between coding and then moving something, maybe a slider or a MIDI controller, always costs a lot of energy of switching the modes, so I wonder what your experience with that is.
I think personally I haven't had so much of an issue with that. I think there's more to explore where the different projections offered could be better tailored to which device I'm using. So a tablet is great for pressing those buttons, but it's horrible for entering text. So maybe if I open it on a tablet, it gives me an interface that's ideal for the tablet. If I open it on a browser or on a desktop machine, it gives me an interface ideal for that. And you could extend that to anything. Because it's fairly easy, I think, to add new devices. Anything that can run the state machine and have some way of triggering actions can potentially be a new input device to the system. So, yeah, I'm.
Given the resemblance you have there to the Ableton session view, I'm wondering whether you've thought about going kind of full Ableton and getting in things like scene launching and clip automation and follow actions and things, or providing some sort of API in your language so you can kind of reflect back and alter the grid via the live coding side.
Yeah, it was clearly influenced and inspired by Ableton's interface. I don't use Ableton myself, so yeah, I definitely borrowed a lot of the design ideas from it. I think the idea of being able to launch something like further in time, like Ableton does, would be really neat. But yeah, I haven't as of yet explored that.
Hi. Is that working? Hello. I wondered if you could talk a bit more about the audience visualization, because to me it seems to foreground the algorithms rather than, like, to me the point of code projection is about the interaction with code and less about like whether someone's using JuxRev or like Chop or whatever. And so, yeah, I guess I wondered how you are representing what's going on with the performer and how they're interacting with the interface.
Yeah, that's fair, and I guess this is a bit of a personal thought, but for me, the excitement about showing the code is to be able to show the audience how the sound comes together and what parts are affecting what you're hearing. So for me, I guess the code being able to articulate that is exciting. I understand that it also misses out on a lot of the other things people celebrate sharing their code. Like when I'm just using pre-written code stems, there's a lot more safety, and you don't see the cursor kind of going through the code and the performer's mental process of struggling with reforming it. But I think there's still some sort of transparency about the artist's intention that can come through the code.
Sorry. I guess I'm just struggling with the fact that you don't see the actual interface that's being used, and you don't see how the person is interacting with it, and you don't see that they're not necessarily writing the code live, or what edits they're making, or like if they're making a syntax error or something like that. I suppose that's where I'm struggling.
Yeah. Yeah, I think I could explore more different ways that the interface is displayed to the audience. Right now, it's actually not showing the exact code that the editor would create, because in the case of title, at least, it produces a really big stack pattern that I think is very hard for an audience to parse. So I tried to create a mapping where the code that it shows the audience is a little bit more decipherable, a little bit easier to read, but I think it could be taken further. Thanks.
All right, we have to leave it at this. It seems though very interesting the fact that many question the idea of code and liveness and so on, but there's one thing to say also, that the 2004 manifesto is actually titled Manifesto Draft. So it's still a draft in theory, right? So there is time to work, and it's on, I think, on an open page, isn't it? Is it open, that page? Yeah, so maybe we have still a day and a half to all discuss together and maybe transform that draft into a more version 2020. All right, thank you very much.
Thanks.
That's awesome, dude. Yeah, it was a great time with you, buddy.
Thanks.
Live coding procedural texture of implicit surfaces, Charles Robert.
Hi, everyone. Great to be here. Like Alejandro, I'm going to be talking about work that I first presented last year at ICLC, and kind of going through a continuation of that process, and really talking about a kind of a big mistake that I wound up making that maybe I wouldn't have if there'd been more resistance and more reflection as I developed this particular project. So the project is called Marching.js. It's an environment for doing ray marching in the browser, and I'll get a little bit more into what ray marching is in a second. And maybe I'll just start by showing a little bit of the kind of things that it does. So it's a JavaScript-based system for doing 3D graphics and live coding them. You can also run it as a plugin inside of Atom. And basically, you create this high-level description in JavaScript of a three-dimensional scene, and then it compiles a fragment shader that runs on the graphics processing unit of your computer that renders out that scene. So here's some different examples. We'll actually be talking a lot about this one, because the main contribution that I'm discussing today is procedurally texturing these geometries that can be created. But there's lots of things for combining different geometries together, for doing volumetric renderings of various math equations. And it's all, you can live code and change things on the fly and adapt. So before I get into what's weird about the texturing aspects, I want to talk a little bit about what's different in this system than a typical 3D graphics rendering environment. And this is kind of a recap of some stuff I briefly discussed last year, but I know not everybody was there, and maybe not everybody remembers my presentation with crystal clarity from last year. So basically, in a 3D graphics system, a typical pipeline, you have a geometry that gets created on the CPU of your computer, and then that geometry is subdivided into triangles through a process called tessellation. All the vertices of these triangles are then submitted to the graphics card of your computer. The graphics card then recreates these triangles on the GPU and then projects them onto the screen via a process called rasterization, which is the bottom picture that's represented right there. So you're dealing with lots of triangles and lots of vertices if you want to do manipulations of geometries in this quote-unquote traditional pipeline. Ray marching works a little bit differently. This is actually a picture of a ray tracing process, but it's still illustrative of the basic idea. In ray marching, you have a virtual camera that is projecting rays through every pixel on your screen. So think of this as a virtual representation of your screen or an image plane. And then you sample various points along the ray to determine whether or not any of those points have struck a particular geometry inside of the scene. So you're basically marching along this ray, taking samples at various intervals, looking at the X, Y, and Z coordinates of those points, and if it strikes one of those objects, then you go back to the pixel that the ray traveled through, and you color that pixel according to whatever the color is of the object that wound up being struck. That's a rough description of the process. And it turns out these formulas for determining whether or not a particular point intersects with a geometry they're typically very simple. This is an example of a formula for determining if a point intersects with a sphere in three-dimensional space, and you basically look at the magnitude of that point and subtract the radius. In the case of a sphere, this assumes the sphere is at the origin. And if you get a positive value, that means the point's on the outside of the sphere. If you get a value of 0, that means the point is on the surface of the sphere. This is an implicit surface. And if you get a negative value, it means it's on the interior of the sphere. And these types of functions are called sign distance functions. And so the nice thing about this is that we're basically just doing some math that can run on the GPU. We can take formulas like this and easily combine them in different ways. Whereas with the prior method, the traditional graphics pipeline, if we want to combine geometries or subtract two geometries from each other, now we're dealing with taking all these triangles and all of these vertices and figuring out which vertices are shared by the two different shapes and which ones do we want to discard. And the math becomes a lot more complex, whereas the math for combining shapes and doing interesting transformations with ray marching is much simpler. So to kind of summarize these two different pipelines or two different rendering methods, with this traditional one that you would use with standard OpenGL, you're calculating rotations and different transformations on the CPU. You're taking your geometries, you're subdividing them into triangles, calculating what the vertices are for each triangle, uploading these vertices to the GPU, and then reassembling them. Whereas in ray marching instead, we basically just take one big rectangle, fill our entire screen, and then for every pixel on our screen, we march through, project a ray, see if that ray strikes any object in the scene, and if it does, we return a color value. So I mentioned that the particular work for this research I'm presenting today was looking at the texturing process. And this led to, I thought it was going to be super easy when I first started, and it wound up being a total headache and making me reconsider a lot of how the rendering engine was designed. And so the specific problem here, if we look at this shape, and maybe I'll just show the actual code for this really quickly to see a little bit better what this does. So we have an infinitely repeated field of a union of 3 cylinders, and 2 of the cylinders are rotated on different axes. So you basically get these crosses by combining the 3 cylinders together in one shape, and then we have this infinitely repeated field. And then down here in the animation code, I'm rotating that union, and then I'm moving the repeated field towards the camera. So there's all sorts of transformations that are taking place here. There's the initial transformations on the cylinders to create the cross. There's the rotation that's being applied on the aggregate of those cylinders to rotate the cross as a gestalt. And then there's the taking these crosses and repeating them in this infinite plane. And then there's the moving the plane towards the camera position. And all of these different things have to be taken into consideration when you're doing the procedural textures of these surfaces. And so the problem comes, so ray marching is really inspired, and my work on this project was really inspired a lot by the demo scene community. And so I talked a little bit about the demo scene community last year. It comes out of software piracy and hacking in the 80s and 90s. And basically when people would hack games so that they could freely distribute them, they would tag the games with their digital signature to kind of tell people how great they were at hacking software, maybe give some shout outs to their friends, and then also including some interesting audiovisual art at the beginning of these games that they were distributing. And as time passed, the people that were creating these audiovisual demos decided that that was actually more interesting than the software piracy aspects of it, and it kind of became its own community focused on creating audiovisual art. And there are demo scene events all around the world every year, and over the past few years, there's been some nice intersection that's been happening with the live coding community and the demo scene community, more events that are being held where they're bringing the two communities together, which I think is fantastic. But a lot of the techniques of the demo scene are kind of inspired with particular technical ideas and particular aesthetics associated with them. And these are where I sort of got hung up when I started implementing a lot of these features. So one of the ways, the biggest portals that people use to distribute apps in the demo scene is through this website called ShaderToy. And if I go to ShaderToy here, it's basically social media for sharing shaders. Fragment shaders are the code that runs on the GPU, and it runs once, a fragment shader will run once for every pixel that's displayed inside of your image plane. And so I'll just click on this, the shader of the week. And here's the code for that. It's about 160 lines of code. And all the code that this author worked on is contained within this fragment shader. That's what's being presented here. But behind the scenes, there's a lot of setup code that's involved to actually get the fragment shader to display in this window and transmit important information that's used in the rendering of the fragment shader. But it's kind of abstracted away to solely focus on the shader inside of this file. And I think it's nice for creating these types of demos because you don't have to worry about jumping back and forth between different files, one file that runs on the CPU, one file that runs on the GPU. You can just focus on the fragment shader file. It's easier to read, it's easier to follow the control flow. But when you're doing tutorials for working with these types of ray marching algorithms and signed distance functions, the tutorials all make the assumption that all of your code is going to be inside the fragment shader the same way they're presented on ShaderToy, the same way that if you're doing a demo scene competition and live coding a shader, the same techniques that you're going to be doing there. And so the problem becomes, if we look at the code to actually create a matrix that can rotate a geometry on the shader, this is what it looks like. So it's a pretty big chunk of code. It's optimized to run on the GPU, so it goes fairly quickly. But I mentioned before that when you're doing the shader, it runs once for every pixel on the screen. And so if we have an HD, a 1080p resolution screen, this shader actually winds up being, this function, if I wanted to rotate one geometry, would wind up being called 2,073,600 times per frame of video for one rotation. So you imagine 3 rotations, you're talking about 6 million calls to this function, and it just scales up and up and up the more transformations that you have to do. So even though it's convenient to include rotations inside the fragment shader and be able to call them with there, it makes it easy to read because it's all nice in one file. In terms of efficiency, it really makes more sense to calculate those on the CPU, which is more similar to a traditional rendering pipeline, you can do it once per frame per geometry, and then upload it up to the GPU once per frame also. So instead of doing it millions and millions of times per frame, you can do it once or twice or 3 times per frame, depending on the number of rotations that are involved. But because I was so enmeshed in these demo scene tutorials when I was working on this, like, it never occurred to me that to think about the interplay of these two things. I was just really involved in that kind of aesthetic that they had put out there, and didn't realize the kind of pitfalls that I was falling into by doing all of these rotations and transformations on the shader and ignoring the CPU potential for doing that instead, for offloading it. So I redid the rendering engine, stuck the transformations onto the CPU, and basically wound up creating a transformation matrix that's attached to every geometry in Marching.js and all of the different types of warpings and deformations that you can do, and wound up changing the API because of that. So before, you had to explicitly create a rotation and tell it that you wanted to rotate a particular geometry. Now everything already has a rotation ready to go, and you just call it as a method. And so I think it wound up actually making the API a lot cleaner and neater and easier to read, and also easier to live code by having it this way, as opposed to the previous method of having to explicitly instantiate each of these things. So I added a bunch of different ways to do texturing. These are showing texture presets that are available, where you can basically just say, I want a texture that's the zigzag texture, or the checkers texture, or the dots texture, and immediately apply it to this. You can also create a 2D canvas object, which is an HTML drawing canvas for doing 2D graphics, and then use that to texture the surface of a 3D shape. So if you have familiarity with the Canvas API, you can immediately start applying that to the 3D geometries. You can create your own texture presets if you're comfortable writing the GPU code, the fragment shader code. And one other thing that's added in here is you can do Hydra code. So I can, this is a Hydra sketch that Steven actually created. And basically I can call Hydra just like I would normally inside of the Hydra system, but now instead of applying Hydra to the full rectangle of the window, I'm applying it directly to this fractal geometry that's being presented on the screen. And then I can go there and I can start editing this and live coding and tweaking various changes to it as well. So just to wrap up, the goal of Marching.js in general is to let people kind of experiment with this ray marching techniques without having to dive into GPU programming. And this particular research was to bring texturing to Marching.js, and I really had to refigure some kind of cultural assumptions, I guess, that I had made about how, what the best ways of doing this was based on the tutorials and the existing online resources for doing this type of rendering. And the results are you can now do some pretty, I think, interesting texturing stuff. It's more efficient, and it's also got a cleaner API as a result. And thanks, and I'll take any questions.
Very cool. Thank you, Charlie.
Yeah.
So at the beginning, you presented part of the motivation for the work as a whole in terms of escaping the traditional graphics pipeline. And then, so in ray marching, right, you end up composing this massive fragment shader that sort of runs for every pixel on the screen, right? And now you have been talking about realizing that you can do things a little bit differently. And I guess the question that I have, and I have a personal interest in the question, of course, is what you think then of the potential also for kind of like taking this back to a little bit of the traditional pipeline model a little bit too, right? Because in the traditional pipeline model, where instead of rendering the big rectangle on the screen, you're rendering this object or that object, although it does impose a little bit of extra complexity on the person making the system, it's a massive optimization for the GPU.
So, yeah, a really common way to use ray marching is to just stick a bunch of cubes on the screen with the regular pipeline, and then you texture it using the ray marching itself, so that you can do really complex shapes via the ray marching algorithm, but the graphics card is optimized to know when everything gets hit, so you don't have to perform as many tests related to that. If it's calling the fragment shader on that cube, the surface has been struck, and so I'm very interested in that. I'd like to get Marching.js to work as a texturer for geometries in 3JS or other systems. I just haven't quite done that. But yeah, I think it's a really interesting way to approach this problem. Instead of just let the graphics card figure out what's been hit, and then you just make these really cool, interesting shapes inside of that geometry.
Yeah, I mean, I've been thinking about it a little bit for punctual, because I'm aware of how huge the shaders are getting that it gets translated into, and I'm just scared about the complexity of doing the work. But if you think it sounds possible, then that gives me a little bit more confidence.
You can talk to Graham about it. Yeah. This is what he does in a lot of his immersive installations, how he does the rendering, is that exact process. Use a regular OpenGL pipeline and then use a ray marcher to actually draw into those OpenGL geometries.
Great, thanks.
Hello. You can just tell me to read the paper, Charlie, if this says way too nerdy. On the implementation side for the generation of the UVW coordinates, are you using a triplanar projection, or is it a 3D texture lookup?
It is not a 3D texture lookup. I tried like the classic triplanar, and then I tried this other random algorithm that I found on some person's website where he just like hacked through it on first principles and stuck it up there, and it wound up giving me better results. And I haven't really dived in to figure out why that is, but I can send you a link if you're interested in looking at it.
Yeah, thank you.
Yeah.
Hi, so I have two hopefully short questions. The first is, one of my favorite things about fragment shaders is that you can get an explicit reference to either relative or absolute position. So you can use that to do various things to the object. In the case of repeating the unions of cylinders, for example, you could make it so that every third union is something different, or every second to the left is something else. And the same with time, you can make it so that every 5 seconds the shape changes or the texture changes. So is it possible to get an explicit reference or to position or time?
So you can write your own geometry, and there's standard ways to bring in primitive geometries into Marching.js. There's tutorials that walk through how to do that, and then in that primitive definition, you would define how that would actually, using GLSL code, you would define what that transformation would be. But yeah, there's limits to how generic what type of generic fragment shader programming that you can do using this. And really, it's designed to work at the JavaScript level, and not as much at the raw GLSL level.
Great. And the second question is, I really like the idea of offloading some of the work to the CPU, which is better suited for that sort of sequential processing instead of parallel processing. But as far as I know, the bottleneck there is the bus between the GPU and the CPU. And so the only way that I know to pass things from one to the other is through textures or uniforms. So has that been a problem in your case, or have you found a better way of doing that?
It hasn't been a problem yet for me. I haven't run into, so I'm just using uniforms, and I haven't run into that limit. The scenes are maybe that I'm doing are not complex enough. I mean, for one geometry, I'm just sending the matrix up, and I guess typically I'm not rendering that many geometries. I'm rendering maybe a few geometries and then repeating them, and so I'm not usually sending that much. But it could be a problem at some point in the future.
Okay, thanks. Looking forward to seeing this next year.
All right, thanks a lot, Charlie.
Hello. Shall I start? Yeah. Yeah, so we're a bit short of time, so if you'd like to read my paper, I'd really love that. I'm just going to reflect, though, on Emma Cocker's work and also Kate Sicchio's in introducing this strange device here. So I'm here from the ERC-funded Penelope project, which is investigating weaving as a technical mode of existence. We're looking at hand weaving in ancient Greece in particular. So there's Ellen Holisius-Gluck, who leads the project, who's a mathematician and weaver. Giovanni Fanfani, who's a philologist, who's rereading ancient texts to look at the role of weaving in the genesis of discrete mathematics and things like that. Anna Perner, who's an ethnographer, and Dave Griffiths, who's also involved as a technologist and live coder and robot maker. So I'll go straight into introducing weaving. So this is the kind of interface that weavers tend to use these days. So this represents the structure of a weave, where there's a white square that represents the horizontal or weft threads going under the vertical or warp threads. So weaving is basically taking the warp, which is under tension, importantly, and then passing weft threads perpendicular and at intersection points. The weft, of course, either goes up or down. And that's what's represented here. It's a structure where you can see it's like a zigzag diagonal structure, and that's showing the structure of the weave. But along the top, you can see there's colors. This is the colors of the warp, which switches between green and blue, and this is the colors of the weft, which also switches between green and blue. And this is the kind of a simulation of the pattern that you end up with, which doesn't look like the structure. It's an interference between two patterns or three patterns, the patterns of the warp and the weft, and the patterns of the structure, which gives this. And then this is what Victoria, our student assistant, wove during a demo of this structure, and you can see this coming out in the end. But if you look closely, you can also see the structure, this zigzag going this direction as the warp comes to the fore. There's a few important things to recognize about this. First of all, that the result doesn't look like the structure, it doesn't look like the inputs. It's the threads perform themselves. They don't kind of act out what you tell them to do. They have their own life. And especially because of this sort of tensile, because the warp is under tension and the threads themselves have behaviors, they have structure of themselves, the twist and all of this sort of thing. It never quite comes out as you expect, which is something which is particular to live coding in general. Also, this doesn't tell you what to do at the edges, and so here it's quite messy because Victoria's not a weaver, nor am I really. So my edges, my selvage, it's called. So these are decision points when you get to the edges. So not only does the kind of structure isn't particularly apparent in what you end up with, but the structure might actually resolve into a weave that just falls apart. So you have this problem. It's not just like drawing. It's working with structures where they have their own properties, And you might even come up with a structure where you end up with two textiles that come apart and then come back together again. So this is a two-dimensional representation of something which is very three-dimensional and woven. So this is the interface that I've made for this thing. So this is a warp-weighted loom. It's a hand loom. So at this point, I think it's important to set aside the jacquard machine. So people often bring up this jacquard mechanism as the kind of connection between computing and weaving. But actually, when you're hand weaving, you're dealing with the computational nature of the threads directly. So once you have the jacquard machine in between, which is just like an input mechanism, you're distancing yourself from the weave structure. And so in a way, the jacquard machine is the end of the connection between computing and weaving, rather than the beginning. So set that aside. But I've still made another machine, which is, I'll show you in a second, which is semi-automated, but only semi-automated. So this is the programming interface for it. It looks like Tidal, but it's really just basic Haskell in a visual interface to make it more playful. This is that block design that you saw here, the up and down structure. And this is this structure actually woven. So I can write some code that describes the binary grid of a weave structure, and then press buttons to make the loom, line by line, bring up the warp threads to create the shed that the threads move through. So yeah, I won't talk about that. Maybe I'll just go straight to showing you the thing itself. Yeah, okay. I've got a virtual reality device, so you can see what I see. We can all become Alex McLean's now. Right. Okay. So you can see there's some solenoids here, maybe. So these are controlled by an Arduino, thread by thread. They control these, which are called headers. So I can individually control each thread. But these only kind of, oh no, all right. Damn. Make more light, or? Okay, so these only offer up the threads. To actually pull the threads forward, I have to use my hands. And then I have two different wefts here. So it's the same kind of white and blue structure. I might have to ask you to hold the camera, Giuseppe, because my virtual reality device has failed. There's some relays here that control it with an Arduino. But importantly, there's some weights here. So just kind of, yeah, maybe around here. So these are weights. Each thread has its own weight. And when you can see they go up and down with the threads. So this is an ancient design, like thousands of years old. In archaeological digs, you find weights, not exactly like these. These are actually from Japanese braiding, but yeah, the idea of weighing down threads is an ancient technique. Right, so the actual interface I can show here. I can find it. So let's just write a quick up and down structure, repeat it, and every second row, invert it. So this is the basic tabby structure. So you can see as I do this, the threads come forward. I think you can probably see that. Oh, it's upside down.
It's upside down, yeah.
Yeah.
I'll turn it this way.
No.
I'll turn the camera.
Yeah. Okay.
Old style.
Yeah. So so I have a certain amount of time to pull these forward as they're offered up. And this creates the shed. So this is the point of opportunity which Emma talks about, where you can have the opportunity to pass the thread, which I'll do here, and then it goes into the weave, and I can do the next line. Have to be quick, too slow. Getting a bit caught up. I'll do it by hand there. And then I'll pass the next thread. So this is basically a form of slow coding. So if I change this now, I can try and make something a bit more complicated. I'll add an extra thing, and now we have this same zigzag structure. Let's say add another one, so down, oops. Up. And then add them together, cycle that. Oh, that was interesting. Yeah, I'll try and do that. So, but you can hear that it has a kind of rhythm to it, which is quite interesting, I think. You can actually hear the rhythm of the weave itself. Oh, it's the white one next, isn't it? So as I go, I'm kind of following this pattern, but I can also make adjustments to, if I see the weave has some problems, I can try and respond, or I can just ignore what the code is suggesting and just do something else, much like Kate's dances. So I suppose the threads are performing rather than acting out what I'm doing. Yeah, I need to integrate this by just changing. I mean, if I go around this, yeah, okay. Yeah, that's worked. Okay. I think I'm not going to get much time to complete a whole weave. Maybe we can take it to the pub later or something. It's not pat tested, sorry, so we'll have to see how it goes. So just reflecting on this then, this is sort of multiple layers of code going on, similar to what Kate was talking about. We've got the weave itself, we've got the block design, which is the underlying structure, and then we've got a code for generating that block design. So we've got these points of indirection, which create opportunity for allowing ourselves to work beyond our imaginations, and also work as sort of, as Tim Ingold would say, sort of force of flow within the world, rather than sort of imposing our ideas on the world. We're just guiding a process as one sort of performing ourselves, but also working with a weave, which is also performing itself, and code, which is performing itself too. That's fine. And yeah, so, and the more kind of layers of, well, one thing I haven't said is that weaving is itself clearly a digital art, because we have these discrete points. We have, it kind of computes the image that you see, and it computes the structure as these interference patterns. And so I think this is an opportunity to really be humbled by ancient technology and learn more about how something like code actually acts upon the world, and also how we can use code as an interface when it's just a partial representation of what we're actually dealing with. Because all code is a kind of abstraction, so it always leaves things out. When we're writing music with code, we don't actually, the code doesn't represent what we hear. It's just like something which is a step in a feedback cycle, that bricolage process. So I'd just like to finish with a quote, as Joanne can't be with her. I thought I'd quote from one of her quotes within her paper, Spaces to Fail In. So this is an anonymous interviewee. One person interviewed spoke about code as a way of working through their daily life, adding structures to it and providing functions for being. These lived patterns merge with her daydreams and expressions of colour and geometry to form her live-coded visuals. So it's kind of, thinking of live coding as being an embodied experience, something which it sort of extends, it's a way of living in a way. It's kind of, it's a way of interacting with the world through pattern, where pattern is just a synonym for computation, I think. I think I'll stop there. If you'd like something a bit more coherent, then please read the paper, and happy to receive your question. Thanks.
It's actually good to end with Joanne.
Yes.
Who couldn't be here and sends her best regard to all of you.
Yes.
Hi, Alex, thanks for that. One question that this brings to mind for me is, given that weaving is such an embodied practice to begin with, that it's manual, that it's done with the hands, that there was no computer involved in its invention, and that it already has a certain utility in encoding both the creative aspects and informational as well. What's your thinking on what bringing code and computers into this dialogue? What is that adding to the discussion, or to the practice?
Yeah, I suppose it's kind of bringing out code in a way, because although it's thousands of years old, and what we understand to be computers weren't around then. Actually, you are a computer when you're weaving, you're computing things. And there is code going on, but it's going on inside your head. These calculations, like having to avoid prime numbers, or having to repeat things, or work with pattern to do these transformations, or this counting. So there's computing there. So I think my role in this project is to try and bring that out and make it visible. That's why Ellen invited me and Dave to be involved, is that she saw in live coding this kind of sort of live practice which shares sort of part of the thinking behind a computational creative performance. And Ellen wanted that for weaving, just to share the, try and share the thought processes of weaving. So I'm not making a claim that, I suppose it's all about pattern, isn't it? So maybe weavers do have this kind of transformation in their head when they're working, but not exactly like that. It's about having respect for the loom, which it doesn't look necessarily that respectful, but it's trying to communicate what's going on behind it. In this instance, I'm trying to communicate the complexities of weaving to live coders inside 10 minutes, which is difficult. But the broad aims of the project are just insert weaving into the history of science and technology in general. And so using contemporary points of view on mathematics to sort of show how weaving itself is computational, I suppose, is the aim.
Alex, you mentioned earlier about edge conditions. I'm thinking, how much does the code, or how much could the code, or how much would you want the code to actually protect you from bad weaves or weaves that can't kind of hold themselves in place? Or is that something you think should be kind of the human side of the process?
Yeah, I think definitely the latter. I think you could, I mean, what looms tend to do is just do a band of a plain weave on the side so it doesn't fall apart and that sort of thing. But for example, this is in the paper actually, how this is a bit of live coding. One moment. Didn't have time to do live coding because it's slow coding. Is that upside down now? I'm confused. Yeah. Okay. So you can see how I've started here with one pattern and then edited it and sort of come across a problem where I've started having these long threads. And this is something that you really try and avoid in weaving because that's when your weave starts to fall apart. And so I was trying different things to get rid of them. They just kept getting longer. I kept making mistakes. And in the end, I realized actually it was really nice and it does hold together. And that it just has this floating thing forming these nice sort of knots on the surface. And this isn't actually a loom for producing fabric, but learning about it and communicating about it. I mean, unless you want a bookmark, it's not going to be very useful. So actually bringing out these edge conditions and exploring them for their creative potential is part of the aim. But yeah, as computer scientists, you see this as things like the salvage as being a problem to be solved. And it's something that, as a weaver, you do learn how to solve it through heuristics. But there's lots of different ways of solving it. And yeah, so the problem with the jacquard loom is that it's kind of a solution for weaving. So you can draw something in Photoshop and then use a loom as a printer then, because it's kind of solved all these problems of float control and stuff. But then the only way of doing that is by completely cutting off most of the creative potential of weaving. So you end up with something that's just like a printer. You see lots of digital artists coming at weaving and just taking an image that they've made and printing it out and calling it a weave. But they're not actually engaging with the structure of the weave, which is three-dimensional, it's not two-dimensional. And to actually solve weaving in that way, you'd have to actually completely model the behavior of the thread, and it would probably be computational intractable, really. So something that seems so simple on the surface has a lot of complexities to it, and once you try and solve these little issues, you just get more and more until you realize that you need to come at it from a more humble point of view.
All right, we have time for one last quick question if you want to, or all right, Kate.
I guess just like going off of that and the edge cases and like this idea of like, yeah, the jacquard loom like doing everything for you. Does that mean like the jacquard loom is kind of like the Ableton Live of weaving?
I'm not sure if I have, I can, I think the question stands on its own, really. Yeah, it is something which gets in the way. I'm not sure if that's true of Ableton Live. It's just Ableton Live's fairly, just everyone uses it. With the jacquard, it's people who don't use the jacquard loom see it as this sort of magical part of this creation story of computing, whereas it's really not. It's just like a way of having pegs or holes go into a machine in order to, and it's not even the first instance of that. It was just pushed very heavily by the French government. So yeah, I think it's a bit different, but yeah, I can understand the feeling.
All right, thank you very much, Alex.
Thanks.
All right. Thanks to all the speakers. That brings to a conclusion the 2 sessions of paper. So now we have a short break, and then there is a lunch concert again at 1 to 2, and then workshops, and then gig again tonight. So thank you, everyone.